Hello everyone and welcome to Lab 5. So today, as you can see, we're going to learn about network theorems. So especially there are three theorems that I'm going to be talking about. One is reciprocity, one is Thevenin, and one is maximum power transfer. So maximum power transfer is something that we are going to do later on, but today we are going to focus on reciprocity theorem and then Thevenin's theorem, okay? So what is reciprocity theorem and what is Thevenin's theorem? So before I go to that, let me just give you a practical example. Let's just take this figure as an example, all right? So you are seeing that we are supplying a voltage from here, and then you can see an ammeter, which is a multimeter for our case, is hooked up over here and here, right? So because of this 10 volt, obviously a certain current would pass through this branch. And then what's gonna happen is I'm gonna interchange this ammeter and then this voltmeter, then this voltage source, you can see. So this voltage source would come over here just like figure 2, and the currents and the ammeter would come over here. We are going to exchange that, and if you see the current that was flowing through this branch, if that's equal to the current through this branch now, then that will establish your reciprocity theorem. And that's why it's written over here as if a voltage source E in one branch of a reciprocal network produces a current I in another, then if the source E is moved from first to the second branch, it will cause the same current in the first branch, where the EMF has been replaced by a short circuit. So there you have it. That's the reciprocity theorem, okay? And what is Thevenin's theorem? Thevenin's theorem is nothing but a way of solving a complex circuit. So what do I mean by that? So when you have multiple voltage sources or current sources, let's say your circuit has a multiple current source and your circuit has a lot of combination of the resistors, right? So because of Thevenin, you can represent that complex circuit in terms of a voltage source, which would be in series with the resistance. And what do I mean by that? If you go to figure 3, you are going to see this complex circuit has been represented by a single voltage source, and this RTH, which is my Thevenin resistance, is just like this one, okay? And then your load resistance will always be there. So load resistance is a very important part, because when it comes to Thevenin theorem, so what we do is we basically, let's see, the load is for over here. Let's just for a moment say that this ammeter is not there, okay? So you have this circuit, you have the potentiometer from going from A to D, and just like this one. So if you measure the resistance, if you measure the voltage across AD terminal, which would be your open circuit voltage, so that would represent your Thevenin voltage. Similarly, when it comes to calculating the Thevenin resistance, what you have to do is replace this voltage source with a short circuit, and if there was a current source, then it would be an open circuit, okay? So now there is a voltage source, so you have to replace it with a short circuit, and then you have to see what's the equivalent resistance across the terminal AD, the node AD, okay? So whatever the resistance you have, that would be your RTH, that is your Thevenin resistance, and you would put it just like this one. But the load resistance that you have over here, right? So that's gonna be still the same. So your load, so all these measurements of this Thevenin circuit particularly, that's gonna be measured across your load resistance, okay? Load resistance terminals. So for our case, that is A and D. And remember, like when we do this measurements of, Thevenin voltage and Thevenin resistance, then our load resistor, that always has to be taken out of the account. That means that we are going to disconnect this RL. So we are just going to have this branch AD. So the voltage across the node AD would be our Thevenin voltage while it's still connected. And after replacing this voltage source with a short circuit, and then if I measure the resistance across AD, that would be my Thevenin resistance. So this is what we are going to do in this lab. And regarding when it comes to the calculations and curves and discussions and conclusions, So there are a couple of things you guys have to do. So everyone, so I have summarized what are the pictures you need to have in your discussion sections. Okay, so there are going to be total 4 pictures for this one, which is current through BC in step 1.1 figure 1, current through AD, and by AD I mean through node A and D. Okay, going from the current going from node A to D. So that would be in step 1.2 figure 1, and from here you are going to have to establish your reciprocity theorem. And if there's a difference, for example, if there's a percentage error, then what might be the cause? You have to state that. That's your step 5.1. You can see that's there in the discussion section. And then there's gonna be the third picture is gonna be during discussing your Thevenin's theorem, which is your in Thevenin's theorem. If you remember, we take 2 readings. One is the open circuit voltage, and another one would be the Thevenin resistance that you take, which so with the help of this 2, you just represent an equivalent circuit, right? A complex circuit to an equivalent circuit. So while you do that in step 2.1 and 2.2, you have to take the readings of that, and I added a footnote over here, which is while you are doing the Thevenin circuit. Then for both cases, if you observe, you're gonna see there is an ammeter and potentiometer, which is your load for this circuit. Okay, so those 2 has to be disconnected from the circuit, because while you were measuring, ammeter is not a source. It's just a way to calculate your current that's passing through from one node to another, right? So ammeter is out of the equation for this one, but while you have the load, which is RL, so that's the terminal you have to focus. And while doing the calculations of VOC, or while doing the calculations as well as the measurements of VOC and RTH, what you have to do is you have to you need to have your RL disconnected. And in the discussion section, what always also you have to do is you take the reading of VOC, you take the reading of RTH with the help of multimeter, right? And after doing so, you need to know, I guess all of you know how to how to represent an equivalent circuit, how to represent a complex circuit into an equivalent Thevenin's equivalent circuit, right? So if you know how to do that by hand, which I'm guessing that you already do, you have to measure VOC and RTH as well. By measure, I mean obviously calculated for this case. So you take the values with the help of multimeter that goes as a measured reading, and then you take you calculate the VOC and RTH by hand. So when you do that, you have to attach the calculations in the discussion report as well. Okay, that means for your VOC, there is gonna be a measured value, and there is gonna be a calculated value. And then for your RTH, there is gonna be a measured value, and then you have to calculate by hand what is your RTH. That's how you have to justify. Okay, and then comment, obviously don't forget to comment on the percentage error. I guess that would be all for this lab. And then like I said before, when it comes to power transfer theorem, so what happened to me is when I measured the open circuit voltage, it comes as a value that is below 4.5 volts, right? So if you remember, through Labrador, we can the minimum voltage that we can supply is 4.5 volt. So as my measured voltage, which is VOC, was less than 4.5 volts, so I have to find a way to make the circuit in a way that you can also do the power transfer theorem with the help of that. Because if you see, you're gonna observe that based on our Thevenin's equivalent circuit, this readings or this justification of the maximum power transfer theorem comes as per our lab manual, right? So for the power transfer theorem, I'm going to coordinate with the other TA. Then we are going to come up with a circuit that has the open circuit voltage, or I would say the Thevenin voltage, at least 4.5 volts. so that we can measure, then complete the readings of the maximum power transfer theorem as well, so that you guys will be able to practice that in lab. Okay, and I'm gonna conduct this portion of today's lab in a separate section, but don't worry about it. So just concentrate on this first two steps, which is the Thevenin's theorem. That's one, and another one is the reciprocity theorem. So that would be all for today's lab. Thank you, everyone.